Hello, everybody. It is time to put behind our study of the general astronomy. That's what we've done so far in Unit 1, and start with Unit 2, the subject-specific content for Astronomy 152. We're going to begin our study with the stars. And if we're going to study the stars, we should really begin with the closest star, the star that we know the most about. So we're going to begin our study of the stars with a specific study of the sun. That's what Unit 1, Part 2, or Unit 2, Part 1 is all about. It's all about studying our sun and studying our sun as a star. When you go outside at night and you look up into the heavens and you see all the stars in the sky, each one of those stars is a sun. Or you could really just think about it. Our sun is just like one of those stars. We could leave our solar system and go several light years away, tens of light years away, turn around and look back on our solar system, and our sun would just look like another star amongst all the other stars. There is more in common between the stars than there is difference. But we know the most about our star, the sun. And what we're looking at here is the sun in ultraviolet. It sort of hits all the exciting things about the sun all at once. You can see all of this interesting activity happening. That the sun is not this calm, quiet thing, but it is quite violent and has all sorts of things happening on it at all times. You can even see a solar flare going off. We will end by talking about the solar activity. I want to begin by looking at our sun as a star. And it is a pretty profound thing to be able to say that the sun is a star. It took humanity a very long time to realize that the sun that's giving us daylight every day is pretty much the same thing as all the stars in the sky. This is what our sun looks like today. This is the 12th of October, 2020. Not much going on. We are at the start of a new solar cycle and a solar minimum. All of that will make sense as you progress through the videos that I'll be releasing on the sun. So the sun is a star, which begs the question, what is a star? And a star is a ball of plasma and gas held together by gravity. So gravity is what holds a star together and pulls it into a spherical shape. And what makes a star special is that it is producing its own energy. A star is producing light. A star shines because it is producing a vast amount of energy. And it produces that energy through nuclear fusion in its core. So there are fusion reactions occurring in the cores of all the stars, which is powering the stars and giving them the energy to shine brightly and give us our daytime right here, or to give us the stars shining in the sky, which we can see for light years upon light years of distance. Okay, a star is a ball of gas, is usually what you hear, but notice I put plasma. Most of the material in the sun is what we would call a plasma. You grew up probably hearing about the three states of matter of solid, liquid, and gas. There are more states of matter. And one of those other states of matter is what we call a plasma. And a plasma is a charged gas. It is a gas where the what's making up that gas are ions of atoms. So atoms that have lost one or many of their electrons. So you have electrons floating around, and you have negatively charged electrons flying around, and you also have positively charged ions. And that collection is called a plasma. You can think of it as a charged gas. And a star emits its own light, it creates its own energy, and it's powered by nuclear fusion. And these fusion reactions are happening in only a specific region of the star, in the central regions in the core of the star. At this point, this number still, it blows my mind every time I think about it a little bit too hard. But if we take all the mass in the solar system, pretty much all of it is the sun. The sun accounts for about 99.8% of the entire mass of the solar system. So if you want to talk about our solar system, we're basically a sun with little tiny leftover bits that are all the planets and the asteroids and the Kuiper Belt objects and everything else in our solar system. 99.8 of the entire mass of the solar system is in the star, which means that stars are much, 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 much bigger than all the planets. Just 0.2% for everything else. And out of that 0.2%, 0.1% of it is Jupiter, leaving 0.1% for everything that's not the sun or Jupiter. Let's just talk about some of the physical characteristics. As I just said, stars are enormous. How enormous? So let's look at the size of a star. We measure the size of stars just like we measure the size of planets. We measure them by their radius. Stars are spherical in shape, so we would measure how big they are from their center to the and take the distance it takes to go from the center to the surface, the radius of a sphere. And the radius of the sun is 696,000 kilometers. That's about 430,000 miles. And here we're going to have something that's really useful. Whenever we talk about the other stars, we always relate them to our sun. So if we're going to talk about the size of other stars, we talk about in terms of how big are they compared to the sun. So we introduce a new unit here. We measure the size of the stars using units that we call solar radii. How big are you compared to the sun? We set one solar radius to be equal to the radius of the sun. So the sun has a size of one solar radius. Okay, so that's one way to talk about how big it is. If it contains 99.8% of the mass of the solar system, how much is that mass? How massive, how much stuff is in the sun? The sun has an incredibly large amount of mass of 1.99 times 10 to the 30th kilograms. For comparison, the Earth is 5.97 times 10 to the 24th kilograms, making the sun 1 million times more massive than the Earth. And it's 1,000 times more massive than Jupiter. So it is a truly massive object. Whenever we compare it to other stars, there are stars out there that are much, much, much more massive. And then there are a lot of stars that are much, 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 much less massive. But the mass of our sun, now, I would like you to be able to recognize these numbers, but I'm not going to ask you to cold write them down. But you should be able to pick them out of a lineup. So a multiple choice type question. But the mass of the sun is 1.99 times 10 to the 30th, about 2 times 10 to the 30th kilograms. And again, we're going to measure the masses of other stars in terms of how they compare to the sun. So we define another unit, what we call a solar mass. And we're going to measure the masses of stars in number of solar masses. Our sun has a mass of one solar mass, which then you could relate to number of kilograms because one solar mass equals 1.99 times 10 to the 30th kilograms. Okay, so just checking off some of the properties of our sun as a star. We're starting to see that it is a pretty extreme thing. Stars are quite large. So let's talk about another property of the sun, the surface temperature of the sun. The core is going to be much, much hotter, but whenever we look at stars, we're looking at their surfaces. I mean, it's a ball of plasma and gas, so it doesn't have a solid surface like the Earth does, but it does have a visible light surface that we call the photosphere. And that light, that's the surfaces, that's where the light that we see, that's where it's coming from. We can take a look at that light as it reaches the Earth, and we could look at its black body spectrum. Because yes, it's a dense ball of gas and plasma, which means that it approximates a black body. You have to consider its atmospheric layers and a couple of other things. Nothing's a perfect black body, and the sun has material above the visible surface that we call the atmospheric layers. But we could go ahead and look at a spectrum, how bright at each wavelength, and that's what you get here in this yellow. When this is going to outer space, so we're not losing any of that light as it comes through our atmosphere, this is what the spectrum of the sun looks like. It's best matched by a black body spectrum that's shown in this shaded gray box, such that they have the same amount of total energy coming out of them per square meter whenever it reaches the Earth. So this black body represents the black body of the sun, and we could go to where that peak is. Found you, you're right there. Figure out what its wavelength is, plug that into Wien's law to calculate the temperature of the sun, and we would find that it has a temperature of 577 or 5,777 Kelvin. For ease of communication, everybody just says that the sun has a temperature of 5,800 Kelvin. So feel free to round the temperature of the sun to 5,800 Kelvin, 5,800 Kelvin. So that is the surface temperature of our sun, 5,800 Kelvin. And now you know how we determine it. We determine it by looking at the sun as a black body. And I just want to reiterate, because we've just introduced a few new things here. We've introduced what we call the solar units, which are going to be the units that we use when we talk about the stars that are not the sun. So we'll compare everything to our sun. So we establish a set of units that are natural for that comparison. We call those the solar units, where we had a solar mass, the mass of which is the mass of the sun. We had a solar radius, which is the radius of the sun. And now, if you really wanted to, although we usually don't go through the trouble, it helps sometimes whenever we work with equations, we could define a solar temperature, the surface temperature of the sun, to be 5,800 Kelvin. All right, so what else can we learn about the sun as a star? Well, if the sun is just a star, if we can determine the sun's composition, and we know that stars out there are very, very similar or more similar to our sun than they are to anything else, then we can pretty much get a rough composition of the stars themselves. So, what is the chemical composition of the sun? What is the sun made out of? And presently, the sun's composition, and I like to go by number of atoms, just count up, hey, how many hydrogen atoms do we have to how many helium atoms to how many other atoms? But you could do it by mass as well. But then you have to know what the mass of each element is, and it gets a little bit more confusing. So I like to stay simple and just count atoms. So the sun's composition by number of atoms, it's 91.2% hydrogen, element number one, created in the Big Bang. So 91.2% of the sun by number of atoms is hydrogen. If you want to do it by mass, that'd be 71.5% of the mass of the sun is hydrogen. A useful thing to consider when we want to talk about the nuclear reactions of the sun. Okay, so primarily hydrogen. Over 90% of the sun is hydrogen. What about everything else? The number two element in the sun is element number two, helium. And it's 8.7% of the atoms of the sun are helium atoms. If you want to do it by mass, it's 27.1% of the mass. So 91% hydrogen, about 9% helium. And if you're doing the quick math in your head, which I know all of you are doing because everybody loves doing quick math in their head, you can go 91.2 plus 8.7 gives me 99.9%. That just leaves 0.1% by number for everything else, all the other atoms in the sun. So what is the sun made out of? Well, 99.9% of it is hydrogen and helium, mostly hydrogen, secondarily helium, and then by number of atoms, just 0.1% is everything else. Now, if you wanted to list those in order of most abundant, most of to least abundant, you would have oxygen, carbon, iron, neon, nitrogen, silicon, magnesium, and everything else. What's amazing is we'll get there later in this semester. We can talk about why these numbers are exactly what we would expect. We would expect to go hydrogen, helium, and then the third most abundant be oxygen, and then the fourth most be carbon, and so on and so forth. And why did I say presently? Well, how is the sun powering itself? Nuclear fusion in its core. How does that work? Nuclear fusion is taking the hydrogen and turning it into helium, and in that process releasing a boatload of energy. So over time, the solar composition is changing. We're losing hydrogen as we convert it into helium. Now you might be asking, how the heck can we know all this? How do we know that the sun is 91.2% by number of atoms, hydrogen, 8.7% helium, and then get all of these other specific numbers? Well, we know by what we spent so much time on, spectroscopy. We actually talked about this whenever we went through and looked and at absorption lines, one of the things that we ended with is by looking at the absorption spectrum of the sun, the so-called Fraunhofer lines, all the absorption features in the visible part of the spectrum from the sun. And in that, you can identify over 67 different elements. And with a careful analysis, by looking at the widths of those lines and other details like that, how big is this line, is a hydrogen line compared to a helium line, and looking at all the very, 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 very fine details, then you can actually determine the relative abundance, how much hydrogen you have versus how much helium you have. So that is how we get after the solar composition. We can determine what's there and how much of each using spectroscopy, using these Fraunhofer lines, where we can go and see this big one right here, that's hydrogen alpha. And then we can find hydrogen beta and gamma, and then we can find helium lines, we can find sodium lines, we can find nitrogen lines, oxygen lines, carbon lines, iron lines, are all within the solar spectrum. And yes, it's a task, but all you have to do is match up where all the hydrogen lines are to this spectrum, where all the helium lines are to this spectrum, and so on and so forth. And then apply a little bit of physics, and not only do you have the composition of everything, but then you have the relative abundances as well. And just to go ahead and show you, this is a different picture of the Fraunhofer lines. Now it's going from blue up here to red down here, so it's reversed its wavelength scale. Well, I just want to show you this one because it has a little bit more detail, and you can actually label some of the lines. Like here's some sodium lines, here's a hydrogen line, a helium line, here's some calcium lines, an iron line. And you can go through this. Oh, here's a mercury line. You can go through this and identify over 67 elements uh, in the Fraunhofer lines. And then we have the UV lines, we have the infrared lines, and all the other parts of the electromagnetic spectrum that we can look at as well to determine the sun's composition. Super cool stuff. Aren't you glad that we spent so much time studying spectroscopy? And aren't you glad that you know a little bit more about our sun already? All right, so let's see here if I can stop the share. My cursor's disappeared. And it looks like PowerPoint has died, but let's see here. So that was all I had for the video. It's going to be a little bit of dead air while I try to figure out since my cursor has disappeared. There we go. All right. So thank you for tuning in. I will see you in the next video.